Okay, then let's move on to the very, very important reaction. This reaction is the heart of this chapter. This reaction is very important. In this reaction, we take our aromatic amine. For example, for instance, let's take here aniline. On this aniline, if we add what we added in the last reaction, if you take sodium nitrite in an acidic medium, for example, if we take HCl and we take that to keep the temperature low, we carry out the reaction at lower temperature, the system is cold, around below 5 degrees Celsius. Then a diazonium salt would be produced. Now this is something we have seen before in the last reaction. In the last reaction, when we took amine and added the same reagent, then we got a salt like this, and later this water that came out during the reaction substituted this nitrogen gas and we got our alcohol. This is what we have done, this is what we have seen, this is what we know. Now the mechanism to reach to this diazonium salt, now azo means nitrogen, azo is for nitrogen, diazo for two nitrogens, and ium is the way we name positive ions like oxygenium, hydrogenium. This here we have diazonium. So this diazonium is for this N2 plus, and this is a diazonium salt. So this was also diazonium salt, and we produced this, and we saw the mechanism how this diazonium salt is produced. And later, because in that reaction the temperature was at room temperature, if nothing is mentioned, that's what you're going to assume. And in that reaction, N2 gas left out this water, attacked, and we got alcohol. So we reported the final product to be alcohol. The difference here being we are keeping the temperature low. Now, and that when the temperature is very low, the movement is all not there. The system is stabilized, the molecular motion, the electronic motion are very, very minimum. So in that case, what happens is nitrogen gas do not come out. Now, even at low temperature, if you vigorously shake the system, this nitrogen gas is such a good leaving group that it will come out. But because the temperature is low and we have stabilized the system, so this nitrogen gas here is not going to come out. So here the salt will remain as it is. This nitrogen gas is not coming out. Nitrogen gas is a very good leaving group. If you increase the temperature even to 10 degrees Celsius, this nitrogen gas is going to come out. Fine. So now what we are doing, we are keeping that nitrogen gas there at its position so that we can replace it when and as we want. For instance, on this diazonium salt, if I add CuCl, now I want this nitrogen gas to move out so that chlorine can come in. If I add CuCN, then I want this nitrogen gas to go out so that my cyanide ion can come in. So what I can do is I can prepare this diazonium salt and keep it as it is, and whatever reagent I add, depending upon that, the replacement of nitrogen gas will happen. Fine. So that's the purpose of keeping the temperature low, so that this nitrogen gas do not move out. Fine. So once the temperature is low and I have added a reagent from outside, so this chloride ion and the cyanide ion, that's going to act as a nucleophile. And now once you have a nucleophile from outside, then no one can stop this nitrogen gas to move out, because you have this nucleophile, and this nucleophile will roam around and will find a position to attack, and which position could be better than this. This carbon would be attacked. Now there will not be any SN2 mechanism because the antibonding is inside the ring. Now this nitrogen gas is so stable that it will leave, and this unstable carbocation will be produced momentarily, and quickly it will be attacked by the nucleophile you have added. Fine. So that's what will happen. It's simple. Nitrogen gas goes out, carbocation forms, this another nucleophile comes in and attack. But it doesn't happen discretely. It happens all simultaneously. As nitrogen gas is moving out, so this nucleophile is attacking. So here the pure carbocation is never generated. So this unstable carbocation is never formed. Nevertheless, nitrogen gas goes out, this nucleophile that you're adding from outside, that comes in. So if you have added cuprous chloride, then this is going to become chlorobenzene. If you have added cuprous cyanide, this is going to become cyanobenzene. If you have added cuprous bromide, this is going to become bromobenzene. Fine. Now, this reaction is called Sandmeyer reaction. Sandmeyer was the one responsible to figure out that this can be done, and this is how we can get various functional group on benzene using cuprous ion. Now the question here comes that this cupric ion cannot be used here. It has to be cuprous, for the reason that cuprous ion can be further oxidized. This Cu plus is oxidized to cupric and it loses one electron. That one electron goes to this diazonium salt to facilitate the removal of nitrogen gas, because when nitrogen gas comes out, there will be a plus charge formed here. When this electron goes into the orbital of carbon, that plus charge vanishes and you get a free radical which is more stable than a plus charge. Fine. When this reaction completes, now you have a chloride, as you have added this Cl minus here. This chloride ion loses one electron to form Cl dot, and that electron goes again. First of all, this chloride ion and this phenyl free radical will combine to give you the desired product chlorobenzene, and this electron is again going to reduce this cupric ion to cuprous ion. So you had cuprous ion, it facilitated the reduction or removal of this nitrogen gas from the salt so that you have a phenyl free radical. The chloride ion that you add, that chloride ion loses electron to become chlorine free radical. These two combines to give you the desired product. The electron lost is gained again by cupric ion to give you again cuprous ion. So that cuprous ion is regenerated, so it acts as a facilitator of this reaction. That's why cuprous ion is required. If you take cupric ion, this mechanism cannot be done, because the first step, if you take already cupric ion, then further oxidation of cupric ion is not possible. So the initiation of this whole reaction is not there. That's why you take cuprous ion. Alright. So if you take cuprous ion, then this is what going to happen. But for iodine, you don't require cuprous ion, because iodine is a very, very good reducing agent. Much better than chlorine, much better than iodine. So being a strong reducing agent, you don't require this facility provided by cuprous ion. Iodine can do it all on its own. So you just use potassium iodide. You don't have to use cuprous iodide. If you take potassium iodide, then the reaction would be there. So you have to keep in mind that these three, chlorine, cyanide and bromide, require cuprous ion. Iodine do not require cuprous ion, and these three reactions are Sandmeyer reactions.